welcome everybody to Jodrell Bank Discovery Centre this afternoon. My name is Mary and I'm an explainer here. So like I said, I'm going to give a quick talk about the history and the science that we do here at Jodrell Bank. So Jodrell Bank Discovery Centre is part of the larger Jodrell Bank Observatory, which includes all these buildings behind you and our three main telescopes. We have the 42-foot telescope, which is just behind you on top of there. The Mark II telescope, which you might have seen as you were walking up towards the sea, a big sort of oval shape. And then, last but not least, the one that we're most famous for, which is the Lovell or the Mark I telescope. So, can somebody tell me, if I were to ask you to describe a telescope, what would you tell me a telescope looks like? Any ideas? A tube? Yeah? You might have said it's a big long tube that you put your eye to and you use it to look into space. So you might have noticed that this telescope doesn't look like a telescope that you might have originally thought a telescope would look like. And that's because these kind of telescopes look at a different kind of light. So our eyes are sensitive to all the colours of the rainbow, all the way from red to about purple. And that's the kind of light that we see through these ordinary telescopes. But there are kinds of invisible light. So kinds of invisible light that come way before red and kinds of invisible light that come way after purple as well. And you might have heard of some of these kinds of invisible light, so microwaves, so what comes out of microwave ovens, they're kind of invisible light before red. And if you've ever been to the hospital and had an x-ray, that uses a kind of invisible light just after purple. And we use a kind of invisible light here at Jodrell Bank called radio waves. And it's because we're looking at a different kind of light that our telescopes look quite a bit different to what you would imagine the telescope would look like. So we can't really talk about the Lovell telescope without talking about the guy who started it all, and his name was Sir Bernard Lovell. And he studied physics in Bristol in the 1930s before coming to do research on cosmic rays here at Manchester. But it wasn't long after he arrived in Manchester that he was eventually called to help with the war. And what he was helping with the war was he was helping to develop radar technology. So what radar technology is you have a piece of equipment and you send off some radio waves, maybe into the sky. And if there are enemy aircraft in the sky, the radio waves will reflect back and give you a signal. And depending on what that signal looks like, how long it's taken the signal to get there, you can work out how far away an object is, how big an object is, or how many different objects there are in the sky. So this kind of technology could be used to look at these enemy aircraft and keep everybody safe. So that's what he was doing just after he'd arrived here in Manchester, working on developing this technology and making it better. But all the while he was thinking about how he could use this technology to study space and study the atmosphere. What else could he use this technology for? So all the time he was doing this research during the war, he was constantly thinking about space, thinking about how he can take it back. So eventually, after the war, he did come back to Manchester to kickstart his research again, and he'd got some of this equipment that he'd taken that they didn't need anymore. And he decided to set himself up in the centre of Manchester to try and look and see what he could see with his radar technology over there. But it quickly ran into a problem, and that problem was that at the time they had these electric trams running right through where he was based, and these electric trams, there were sparks coming off the tram lines, and those sparks were giving off radio emissions. So when he set his equipment up, that's all that he could see was this noise from the tram lines, these sparks. So he went to the university and said, I'm trying to look, but I can't see anything because of these sparks. They're interfering with my equipment. Is there anywhere that I can go where I'm not going to get any of this interference, where I can sort of look without worrying about anything else? And they said, we do have a site and it's called Jodrell Bank, and it's owned by the botany department, but you can go for 3 weeks and then you've got to leave. So obviously it's not ended up that way in the end. He stayed just a little bit longer than 3 weeks, but he did go and he came to the site, and like I say, at the time the site was dedicated to the botany department, who were doing some really interesting research on potatoes and carrots. And one of the things they were looking at with carrots is they wanted to know the best distance between carrots. So if your carrots are too close together, then they're going to sort of interfere with each other. They're not going to grow properly. But if your carrots are too far apart, then you're wasting some perfect and good soil. So that's what they were doing over here at Jodrell Bank. And then Bernard Lovell turned up and set up his equipment and started to look into the sky to see what he could find. And one of the very first things he was able to look at with his equipment was shooting stars. Has anybody ever seen a shooting star before? Yeah, a couple hands. So a shooting star, the name is quite misleading because it isn't actually a star. What it really is it's a chunk of rock that's travelling very, very quickly through the atmosphere. And as it travels quickly through the atmosphere, there's a lot of friction and it heats up. So we can demonstrate that. So if you get your hands and put your hands together and then rub really quickly, you'll feel that your hands start to get quite hot. And it's the same reason that your hands get hot when you rub them together very quickly, that these chunks of rock get very, very hot as they're travelling very quickly through the atmosphere. So these rocks, they burn very, very hot, and then they leave behind a bright streak, and it's that bright streak that you can see in the sky when you see a shooting star. Now, it turns out that these bright streaks that are left behind reflect radio waves. So when Bernard Lovell had his equipment and he was sending his radio waves into the sky, these were reflecting his waves back at him, and he was detecting them, he was picking them up. So he got himself a buddy, and he was sat with his equipment, and his friend was sat in a deck chair looking at the sky, and they could match up what his friend was seeing with his eyes with what he was seeing with his equipment, and being able to prove that you can use this radar technology to actually study space and further. So that was one of the first major successes of Bernard Lovell's work. But it wasn't long after this, he'd taken over the site, and all the botanists had gone, and he decided he wanted a more permanent telescope. And one of the first telescopes he built was called the Transit telescope, which was a huge field full of wires, just on the field. There wasn't any sort of dish or anything like that. It was just a bunch of wires. But what this telescope was able to detect is the nearby Andromeda galaxy. So the Andromeda galaxy is the nearest galaxy to our own, and it's 2.5 million light years away. So that's a very big distance. So what a light year is it's the distance that light can travel in 1 year. So when light travels, it doesn't come instantly. So the light that comes from the sun, which is it's showing its face today, that takes 8 minutes to get here from the sun. So a light year is the distance that it travels in a year. So if it only takes 8 minutes to get here from the sun, you can imagine how long a whole light year is. So I can demonstrate that. So if I were to hold, so if in my hand I had the Earth, and in this hand I had the sun, a light year would take you to the centre of Manchester. That's how far that is, if you can imagine. So it's quite a big distance. So Andromeda is 2.5 million light years away. So a light year, about 10 trillion kilometres, that's 2.5 million times 10 trillion kilometres. It's so far away. And the other thing about things being light years away is because it takes a whole year for light to travel 1 light year. If you're looking at something that's 2.5 million light years away, you're actually looking at it as it was 2.5 million years ago. So looking into space with these telescopes, you're actually looking back in time. That light takes time to travel to us. So what Andromeda looks like right this second, we can never know because it takes time for that light to reach us. So that was one of the things he did with this very early telescope, the Transit telescope. But of course he was very ambitious and decided this telescope's not good enough, we can't steer it. When you have these telescopes that are based on the ground, you have to wait for the Earth to turn to point at something new. So he decided, I want a telescope that's fully steerable so I can point it at whatever I like, whenever I like. And that's when he drew up plans for the Mark I. So the Mark I, the Lovell telescope, it's still the 3rd largest fully steerable telescope in the world. and at the time of building it was the largest in the world. There's only two bigger. There's the Eppelberg telescope in Germany and there's the Green Bank telescope in the States, and they're about 100 metres across. So the Lovell is 76 metres in diameter and, as I say, still the third largest in the world. So he started building this telescope in the 1950s, but ran into another problem, and that problem was money. His original budget was about £150,000, which even today that's a lot of money, but back in the 50s that was a lot of money. And he went 6 times over budget, and he'd not finished the telescope yet. So he'd run out of money, he couldn't pay the construction workers to continue building the telescope, so it was looking very bad indeed for the Lovell telescope. But in 1957, it was saved because of the launch of the SPUTNIK satellite. So the SPUTNIK satellite, launched by the Soviet Union, was being carried by a missile. And the government wanted to be able to track this missile, because there's every chance the same missile could be used to carry something like a nuclear bomb. So people were sort of saying, I think we should be able to look at this and track it where it goes, just to be safe. If we could track these things, that would be great. But it turns out the only thing that could have done that was the Lovell telescope. So all of a sudden, all of the funding comes in, the telescope gets built, the university forgets about all the debt that Bernard Lovell had put them in, and the telescope was built. So almost overnight, the telescope went from an overly ambitious university project to a tool of national security. And the Lovell telescope was built, and it was able to track SPUTNIK all the way into orbit. So a little bit about satellites and launching things. Do you think we have to send things really, really quickly to get them into space, or really, really slowly? Any ideas? Yeah? Slowly? Not quite. Any other ideas? Quickly? Yeah. Does anybody want to do we've got a rocket here. Would anyone like to be the volunteer to launch into space? I think your arm went up first, but if anyone wants to have a go after we finish the talk, then you're welcome to. All right. What's your name? Time. So we're going to do a countdown from 5, and when we count down, I want you to stomp on that pink thing as hard as you can. Ready? 5, 4, 3, 2, 1, go! So we have to launch things very, very quickly to get them into space. Now, the other thing you might be thinking about satellites is they stay in space. So what is it that keeps them up there? You know, when I jump up, I come straight back down to the Earth again, and that's because of gravity. So what is the reason that these satellites don't come back down again? And again, the key is speed. They're going very, very quickly around the Earth. So I'm going to prove here that you can go really quickly, then it won't fall down, by tipping a cup of water over my head and staying dry. So, in here I've got some water, so proving that I'm not phony. And I'm going to tip it over my head on this tray. Who thinks I'm going to get wet? Yeah, think I'm going to get wet? Yeah. Okay. Are we ready? So because I'm spinning the tray really quickly, the water hasn't got time to fall down onto my head. So I'm staying dry, the water's still in the cup, and that's how satellites work. So I'm still dry. And that's how things like the International Space Station stay in orbit. They're going too quickly for gravity to hold them down. So the SPUTNIK satellite, the world's first artificial satellite, was tracked by the Lovell telescope, but the Lovell telescope was able to track something else as well, and it was the Lunar 9 mission. And the Lunar 9 mission was sent to the moon, and it was to test a soft landing. So if you wanted to send astronauts to the moon, or anywhere for that matter, you want to make sure that when you come down onto the surface, that it's a nice soft landing and it's nice and safe, so no astronauts get hurt on the way down. So that's what they were testing with the Lunar 9 mission, and Bernard Lovell said, I want to track that, and I've got the kit to do it. So he did. He tracked it all the way to the moon, and then he started picking up a funny signal. And he said, that signal looks very, very familiar. So he called up his friend who had a fax machine and said, can I plug my telescope into your fax machine? And he did. And this signal went through the fax machine and out popped the first photograph from the surface of the moon. So Lovell had managed to track this rocket all the way to the moon, steal the very first photograph and have it published in the local newspaper the very next day before the Russians had a chance to do that. So they were a little bit mad, but that was another success of the Lovell telescope. But of course, the Lovell telescope wasn't necessarily built for tracking space race or for tracking tracking things. It was built to look at space. It was built to look at things in space. And a lot of the things we look at in space are objects like stars, or the things that come from stars. So the sun that we see today, that's a star, and all these stars start off as a huge cloud of gas. So a huge cloud of hydrogen gas in space. And then all of these gas particles, they come together under gravity, they get closer and closer and closer and closer and closer, and then eventually they start doing what's called a nuclear fusion reaction. And this reaction, it changes the hydrogen into helium and gives off lots of energy. So it's coming down because of gravity and then expanding out because it's giving off lots of energy. So stars stay about the same size for their whole life. And that's the heat that we feel today because of the sun. It's that energy that's coming from these nuclear fusion reactions in the sun. So our sun is about average size for a star, and when stars that are like the sun die, what will happen is the core will collapse, and then the outer layers of gas will expand and expand and expand and expand. And when that happens to the sun, it's not for a very long time, so it's something you have to worry about. But when that happens to the sun will expand and swallow Mercury and Venus and even a little bit of the Earth, maybe. So it gets very, very, very big. And it forms a very, very dense core right in the middle. And that dense core is called a white dwarf star. And these white dwarf stars are really heavy. So the white dwarf that will be left after the sun's died will be about the same size as Earth. So all of that stuff that was in the sun has been compressed and compressed and compressed into something the size of the Earth. So if you were to get a teaspoon and then go up to a white dwarf and scoop up a bit of white dwarf, your teaspoon would weigh more than 5 tons. So that's the same as having 5 elephants in your teaspoon. So they're very dense objects. But there's something that can happen if you've got a star that's more than 8 times the size of the sun. These even heavier stars, they do something different. They keep on doing these nuclear fusion reactions, and they get very big, and then eventually they collapse in on themselves and do a supernova explosion. You might have heard of the word supernova before. So it's this big explosion that gives off lots and lots of energy, and then leaves behind, again, more dense cores. And when these really heavy stars die, they can form either a neutron star or a black hole, which you might have also heard. So the first of these things, these neutron stars, again, very, very dense. All of this stuff that was once a star has been now compressed into something the size of maybe Manchester. So again, if you were to go up with a teaspoon and scoop up a bit of neutron star, your teaspoon would weigh more than Mount Everest. It's so dense and heavy. But sometimes these neutron stars, they do this really funny thing, and they spin very, very quickly and also have jets of energy coming out of either side. So you can imagine my arms are jets of energy, and they spin very, 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 very quickly, just like that. And that's what a pulsar looks like. And these pulsars are very, very interesting objects. And when they were first discovered, they were discovered by a very incredible lady called Bernard. And when she discovered them, she didn't know what they were. So she had her data from the telescopes, and she kept seeing these regular blips, sort of like spikes in her data, which is a bit bizarre. So the sun, at the minute, you can see that it's not flashing. Stars don't tend to flash. They just give off energy in all directions, all the time, and it's pretty constant. So when Jocelyn saw these flashes, she had no idea what that could be. She didn't know, because we'd not discovered pulsars yet. So she actually nicknamed the first pulsar LGM-1, which stands for Little Green Man 1, because she thought that this signal could maybe be aliens, because it was so regular and we'd never seen anything like it. But it turns out that they're just these neutron stars that spin very, very quickly and give off these large jets of energy. So these jets of energy, it's like a cosmic lighthouse. you've ever seen a lighthouse, you only see it when it's shining its bright torch right in your direction. And that's kind of what happens with our telescopes. If the beam of radiation is pointing exactly at the telescope and it sweeps past, you get a blip. And that's what we see. So the other thing that can form from these supernova explosions is a black hole. So you might have heard of a black hole, you might have also heard that they can be quite scary things, sucking everything in and never letting anything back out again, which is kind of true, but they're also nothing to really worry about. But they are very cool objects. So black holes, they're infinitely dense. They're so dense that even light can't escape. So when the light comes in, like we were saying with the rockets and launching things into space, you need to get them to go so quickly so that they leave the Earth. Well, the speed to get off a black hole is faster than the speed of light, and it's not possible to go that fast. The speed of light is the universal speed limit. So anything that goes inside a black hole can never get back out again. And because of this strange behaviour that light has in a black hole, if you were to stand on the surface of a black hole and look straight in front of you, because of the way the light orbits around the black hole, you'd be able to see your own back just on the surface of the black hole. So that's another funny fact about black holes. So black holes, they were studied here at Jodrell Bank, and one of these black holes, so sometimes you can have black holes at the middle of galaxies, and these black holes, sometimes they suck all of this matter in, and it swirls in and it swallows it all up. But it can also give out jets of energy, and these jets of energy, when we have these black holes, we call them quasars. And astronomers at Jodrell Bank were looking at these quasars, and they didn't know what they were, but they were picking up this energy, and they weren't sure where it was coming from, because the source was really bright, brighter than any stars, but also really far away. So it couldn't possibly have been a star, so they didn't know what it was. But they were able to measure the size of these quasars by putting another telescope on a truck, driving it around the countryside, and linking the Lovell telescope up with another telescope. And by doing that technique, which we call radio interferometry, they were able to measure the size of these objects. So that's a little bit about some of the science that we do at Jodrell Bank, but I'd just like to finish with one of my favourite things that we do here at Jodrell Bank, which is look at the crab pulsar. So the crab pulsar is the core of a dead star inside the Crab Nebula that was left behind after a massive star exploded, like any pulsar. But the fun thing about crab pulsar is that in the Crab Nebula, we know where it is. And it turns out we actually have records from 1054, so nearly 1,000 years ago, from Chinese astronomers who described seeing a bright source in the sky that shone day and night for 3 weeks and then went away. It turns out that bright star that they saw in 1054 was actually the supernova explosion of the star that once was the Crab Pulsar, which we still study here with our radio telescopes here at Jodrell Bank even today. So thank you so much for coming to Jodrell Bank this afternoon. It's been wonderful to have you here. And if anybody has any questions, please do come to me at the end. I'm happy to answer any questions. But I hope you all have a great rest of your day, and thanks again for coming.
Yes, I think standing on the surface of the black hole might be a good thing to do.
Yes, it could be. I heard something one day it's called black hole, not necessarily not like, but it's open the galaxy, it's just stuck the galaxy.